Okay, so finally we are going to learn 1.3 factors affecting reaction rate. So our learning objectives will be to explain the effect of the following factors, okay, on the reaction rate. Does it slower your reaction or make it faster when we vary it? Okay, and then we're going to illustrate the effect of temperature on reaction rate using Maxwell-Boltzmann distribution curve. And then we're going to draw the curve of the energy profile diagram for a reaction with and without catalyst. So basically for your EA, when we have catalyst, it will be lower, but without catalyst, it will be higher. Alright. Next, we're going to state the Arrhenius equation and use that Arrhenius equation to relate between temperature, activation energy, and rate constant. And then we're going to do some calculations and draw graphs using the Arrhenius equation to find any of these terms. Alright? So, reaction rate will either slow down or become faster when we change or vary the following factors. Alright, so the first factor is concentration. So concentration is mole of solute over the volume of solution. So the higher concentration of reactant, the more particles of reactant that are present. Right, so when we have more particles, then the frequency of collision will increase. Maksudnya more collisions will occur. So if there are more collisions, therefore the probability to have more effective collisions will occur, right? Okay, so therefore the reaction rate will increase. Next is pressure. So this applies to gaseous particles. So changing the pressure of your gas is similar to changing its concentration. Okay, why is that so? Because if the gas pressure is increased, okay, which is by reducing the volume, the gas molecules will be closer together. So when they are closer together, okay, they will more likely collide with each other because they are in a more compact space. Okay, so more effective collisions will occur and the rate of reaction will also increase. So this is an illustration or visualization if pressure is increased when we reduce the volume. So this is low pressure where you have a large volume. So your gas particles are far away from each other. So the frequency of collision is not as high. Okay, not so high. Okay, so the effective collision will be lower when at low pressure. If you increase the pressure, alright, by reducing the volume, so the volume is much smaller, right? Your particles, they are much closer to each other, okay, in this compact volume. So therefore, the frequency of collision will increase. Okay, more collisions will occur per second, and therefore the more effective collisions will occur. Alright, so the rate of reaction will also increase. Third is the particle size. So this will apply to solid particles. Like imagine you have a cake, right? And then you cut it. So when you cut the cake, you have more surface area. I think you learned all this in Form 5. So when the size of your reacting particles is decreased, okay, maksudnya you cut them, okay, make them smaller daripada a big chunk to smaller chunks, right? The total surface area exposed for reaction increases. More surface area exposed. So therefore, the higher the frequency of collision, therefore more effective collisions will occur. Therefore, rate of reaction also increase. Simple kan? Okay. Next is temperature. So, what do we talk about when we talk about temperature? We will talk about the kinetic theory. Okay. Maksudnya, we will be relating kinetic energy. So, if the average kinetic energy if the temperature of your reaction increases, therefore the average kinetic energy will increase. So these two are directly proportional to each other. So an increase in temperature increases the average kinetic energy of your reactant molecules. So bila awak punya molecules tu dia laju, therefore more molecules with enough energy will collide. So maksudnya awak punya reactant molecules, okay, there will be more reactant with energy equal to or greater than EA, your activation energy. So therefore you will most likely have more effective collisions. Alright, so reaction rate will increase. A graphical way to visualize the effect of temperature on your reaction rate will be by using Maxwell-Boltzmann distribution curve. Okay, especially when you have a general reaction, okay, a reaction mixture at different temperatures, let's say at T1 and T2. Okay, so let's see, this is our Maxwell-Boltzmann distribution curve. Alright, so in your Maxwell-Boltzmann distribution curve, on your y-axis you have number of molecules, and on your x-axis you have your collision energy. Alright, so the blue curve here is the curve, okay, of energy distribution for your molecules at temperature T1. Okay, and the red curve is for temperature T2, where the temperature T2 is higher than temperature T1. Okay, so if you look at the area under the curve, it represents the number of molecules. So this curve, okay, the area under it, this one, is equal to the shaded area under this red curve. Okay, so the number of molecules is equal, alright, for the whole curve, each of the curve. Okay, but if you look here, okay, for temperature T1, at temperature T1, the peak here tells the average kinetic energy for the molecules at temperature T1. So this one will be the average energy, kinetic energy for the molecules at T1. Okay, so maksudnya most of the molecules have this kinetic energy, collision energy. For T2, most of the molecules have this collision energy, okay, kinetic energy. So that is just the average kinetic energy. But now we want to know how much of the molecules will exceed the activation energy, okay, because we want to know how much of the what is the number of molecules that will turn into products. Okay, so molecules that pass this barrier, okay, all of these molecules will have effective collision, so therefore will turn into product, right? Okay, so if you look at temperature 1 punya curve, okay, this is the shaded area. This will be the amount of molecules for temperature T1 that will possess enough energy, okay, to form product that will have effective collision. Okay, and this one is the amount of molecules that overcome the energy barrier and will have effective collision for temperature T2. Okay, so that is a greater fraction of number of molecules at T2 with enough energy to react. Alright, so basically this is what I just showed you just now. So here, this is the temperature 1 with its average kinetic energy at T1. Alright, so most of the molecules will have this average kinetic energy at temperature 1, and this one is the average kinetic energy at temperature 2. So as you can see, the average kinetic energy for molecules at temperature 2 is higher when temperature 2 is higher. So E2 is larger than E1, therefore when temperature increases, okay, the average kinetic energy increases as well. See, this one is much more to the right, so it's higher energy. So the molecules will move faster and more collision occur, therefore more effective collision, thus reaction rate increases. This means that the reaction rate for molecules at temperature T2 at a higher temperature will be higher. Okay, the reaction rate will be higher. Okay, so this one we are going to talk about the number of molecules under the shaded area, at the shaded area under the curve. Okay, so more molecules will react at a higher temperature. So as I explained just now about the activation energy for the different temperatures, okay, the effective collisions occur after this activation energy for these molecules. So these shaded area here are the molecules that possess enough energy, has overcome the activation energy barrier, and will have effective collision. Okay, so I've drawn over for temperature 2 and temperature 1. Alright, so if you can see here, okay, the size of the shaded area for each of the temperature, the shaded area under the curve for temperature 2 right here is much more bigger than the shaded area for temperature 1. So that means there are more molecules possessing enough energy, okay, to have effective collision for temperature 2, the higher temperature, than for temperature 1. Alright, I think you can read this on your own. Okay, next factor is catalyst. Okay, so catalyst, I think you know that it is a substance that increases the rate of a chemical reaction without itself being consumed. So basically, if you have catalyst, your catalyst will not be used up, or if it is used, it will be regenerated. So it doesn't it does not change. Okay, so the catalyst, it provides an alternative pathway which has a lower activation energy, so lower EA, okay, compared to the one without catalyst. So if you add catalyst, this will cause the number of reactant molecules having kinetic energy which is greater or equal to EA will increase. So more effective collisions, therefore rate of reaction will also increase. So how will you draw the energy profile diagram for reactions with catalyst and without catalyst? So on your left, we have the energy profile diagram without catalyst. So this is your EA without catalyst. Okay, you need to overcome this barrier, energy barrier. Okay, but if you have catalyst, all right, it is this one. Okay, this one is already combined, the graph. So if you see here, ECA, this is activation energy with catalyst. Okay, this one here, EA, is without catalyst. So when you have catalyst, you can see that the energy barrier is much lower than without catalyst. Therefore, more molecules are able to overcome the lower energy barrier, thus forming more products. Okay, so make sure to label your graphs neatly when you draw your energy profile diagram. Okay, make sure you have your product reactance axis, delta H, and label EA with catalyst and EA without catalyst. Alright, next, okay, is the Arrhenius equation. So we're gonna use the Arrhenius equation to relate rate constant, activation energy, and temperature. So this is your Arrhenius equation. Okay, so K is your rate constant, R here is your universal gas constant. So basically we're gonna use this one. Why? Because your EA, activation energy, will be in joule per mole or kilojoule per mole. So we want these two to tally. Alright, so we can cancel out when we need to. And E is just your exponent. T is your absolute temperature. It must be in Kelvin. Why? So if it is in degrees Celsius, you must change to Kelvin because the gas constant that you're using is in per Kelvin. Okay, it is in Kelvin for the temperature. Okay, so be aware of the units. Alright, that's important when doing calculation. Okay, so this is your Arrhenius equation, and if you log both sides, okay, you will get this. Okay, so you will use this form of Arrhenius equation to find your activation energy. Okay, how will you do that? We will be using graphical method where we will fit this equation to y equals to mx plus c. Okay, so basically your y-axis will be ln k, your y-intercept will be ln a, and your slope will be negative EA over R. Okay, and your x-axis will be 1 over t. Okay, so the important part is to find EA. So when your slope is equals to negative EA over R, okay, you can find your y2 minus y1 over x2 minus x1 and rearrange your terms here to find activation energy. Alright, okay, we have to use this one, okay, when we are looking for EA using graphical method, because from here it is a little bit difficult because your EA is at up there to the power of your exponent. Alright, I mean to your exponent to the power of negative EA. Alright, so you have to use this one for graph. Alright, okay, so okay, so A, what is A? A is your frequency factor or pre-exponential factor. So this is your exponential factor, this is your pre-exponential factor. Alright, so A will have the same unit as K. Okay, so K, if you recall 1.1, it will depend on your order of reaction lah. Okay, so look at the unit of your K, your A will follow the unit for K. Okay, so A is actually the rate constant if all the collisions had enough energy to overcome the energy barrier. So maksudnya, okay, maksudnya K will equal to A if this one is equal to 1. Alright, 1 maksudnya Why? Because this exponential factor is the fraction of collisions with the minimum energy for reaction. So maksudnya, if all the collisions had enough energy to overcome the energy barrier, maksudnya semua awak punya collisions tu adalah effective, therefore your your exponent will be to the power of 0. Therefore your fraction will be full lah, maksudnya 2/2 contoh, atau 3/3 contoh. Maksudnya it will be equal to 1. Okay, so e to the power of 0 will be equal to 1. Therefore if it is 1, then your k will be equal to a. Alright, this is what this means. Okay, so so for your Arrhenius equation, if you increase your temperature, this one here, the average speed of particles will increase. Why is that so? Because when T increases, therefore your A will increase, so K will increase. Okay? Okay. But if you decrease your if you increase your EA, okay, your activation energy increase, therefore your K will decrease because your activation energy lebih tinggi. Alright? If you increase temperature, maksudnya your kinetic energy will increase. Okay, so your rate of reaction will increase, kan? So if your rate of reaction increase, then K will increase. Okay, so only those collisions with enough energy to exceed EA can lead to reaction. So temperature rise will enlarge your fraction F, maksudnya this whole thing. Okay, with enough of collision with enough energy to exceed EA, and magnitudes of both activation energy and temperature affect the fraction of sufficiently energetic collisions. So EA and temperature will change. If you vary your EA or your temperature, your rate constant will change. Okay, so higher temperature will lead to larger K, therefore rate of reaction increase. If you increase your EA, okay, maksudnya awak punya energy barrier tu lebih tinggi, therefore your rate constant will decrease, maksudnya your rate of reaction will also decrease lah at that certain temperature. Okay, alright, so the first example is the decomposition of N2O5 has an activation energy of 103 kilojoule and frequency factor A of 4.3 times 10 to the power of 13 per second. So this is a first order reaction, okay, per second. What is the rate constant K for this decomposition at this temperature and this temperature? Alright, so for this question, you are given the activation energy, you are given the frequency factor A, and you are given the temperature, alright, in degrees Celsius, and you want to find your rate constant. So you can use your Arrhenius equation and make sure to use the right gas constant, that is 8.314 joule per mole per Kelvin. So just use this and plug in your values, but make sure your units are correct. Alright, your temperature must be changed into Kelvin. Okay, and make sure your activation energy is in joule per mole, so just change this to joule per mole. Okay, this is in kilojoule, change to joule per mole. It must have per mole because activation energy dia kena per mole. Okay, and this one just masukkan je lah awak punya A, and then you plug in your values and you should get these answers. So the unit of your K, your rate constant, will follow your frequency factor per unit, which is per second. So make sure to write down the unit and make sure it is correct. Alright? Okay. Example 2. Rate constant for the decomposition of nitrous oxide N2O into nitrogen molecule and oxygen atom has been measured at different temperatures. Okay, so you are given rate constant per molar per second for these few experiments, and its corresponding temperature in degrees Celsius. So determine graphically, maksudnya you have to plot graph to find the activation energy for the reaction. So you want to find EA. So for this one, you are not going to use K equals to E power of E negative EA over RT, but you will use the one that is already log for both sides, which is ln K equals to negative E over R 1 over T. Ni awak keluarkan supaya awak boleh fit to Y equals mx plus C. Okay. So your y-axis will be ln K, your x-axis will be 1 over T. So basically you have to change this lah. Awak you ln the values, okay, and then find what is 1 over T, okay, and make sure it is in Kelvin, alright, and then you know that your slope will be negative EA over R, okay, your gradient. So you have to find EA from the slope, and this is just your y-intercept. Right? So make sure to do all this. Okay, your temperature must be changed to Kelvin. Find 1 over T. Okay, so this is your y and this is your x. So plot the graph of ln K versus 1 over T, and you should get this kind of graph, straight line graph. Okay, so from the graph, okay, you can find the gradients. Okay, once you get the gradient, you can just rearrange the values. Okay, make sure to plug in your right gas constant. You're going to use 8.314 joule per Kelvin per mole. Okay, because it must tally with your activation energy. Your activation energy is in joule per mole. Okay, so maksudnya kena tally lah, janganlah guna gas constant yang salah. Okay, yang 8.626 tu ke, jangan. Okay, and then just rearrange and you should get your answer. Okay, ni saya dah bagi peringatan. Alright, if we are given different temperatures, let's say you are given T1 and K1, and then you are given T2 but not K2, so then you will be using this Arrhenius equation, but okay, you're gonna put K2 and T2, K1, T1. Okay, so maksudnya for this temperature you will have this rate constant, for this temperature you will have this rate constant. Okay, so if ln K2 minus ln K1, okay, you will get this equation. Okay, so now we can use this equation. Let's say if we are given T1, K1 and T2, you want to find K2, then you just use this equation and then find K2. Alright, you have to know how to rearrange. Okay, alright, so example 3. Okay, decomposition of HI has rate constants K1 and K2 at these temperatures T1, T2. What is the EA of this reaction in kilojoule per mole? So basically you're going to use this formula, okay, and make sure your temperature changed to Kelvin, okay, and just plug in your values and exponent when you want to find your K2 and rearrange je. Alright, okay, sorry, you want to find EA. Okay, okay, so this is the working. So basically like here, like as I said, you have to change to Kelvin. Okay, and then you want to find EA. So you just plug in your values. Okay, make sure you are using the right gas constant value. Okay, and then you can find your activation energy. Alright, remember the unit of activation energy will be in joule per mole or kilojoule per mole. It has to have this per mole. Alright, ingat, okay? Okay, for this example, you are given rate constant of first order reaction. This is K1. This is T1. Change to Kelvin. This is your EA, activation energy. Calculate the temperature, T2, when your rate constant is this, K2. So, macam guna that formula, ln K2 over K1 equals to blah blah blah. And then you should find your temperature being these. Alright? Okay, good job. So, this is the end of 1.3. So make sure to make overview notes. I want you to list down all the formulas, okay, and when to use each of that formula you need to know. And also draw your Maxwell Boltzmann distribution curve and try to explain the curve to yourself. Do you understand it? Okay, so if you don't understand, then you can ask me, okay, or your friends, and make sure to attempt tutorial questions. Alright? Good luck. Thank you, everyone.